So we spent 2 days learning the skill of dividing polynomials by other polynomials. We learned 2 methods for doing that, long division and synthetic. Synthetic is less writing. It's a bit more streamlined. So like it's faster, but it only works when you're dividing by a linear term. It only works when you're dividing by a degree 1 term. But that's most of the dividing that we do. So that's good. Most of the time we can do synthetic. There's one situation where you have to use long division, and that's when the degree that you're dividing by is higher than 1. So if you're dividing by a degree 2 term, a quadratic, you would have to use long division. That's something that you need to know, right? That could come up. On the test, it might say, do the following with long division, do the following with synthetic, do the following. And you would have to know how to do each type. Okay, that could happen. So then we're doing one more sort of preparatory thing today called remainder theorem. And then on Monday when we come back, we are starting something that all of the buildup of the last 3 days has been working towards. So Monday is when the real good stuff starts to happen. So one more day of kind of prep. Remainder theorem is quite simple, quite straightforward. The main idea of it is like just basic, I think. Once you get it, it's easy. And then it's a special case of remainder theorem that's really, really useful that we do on Monday. A special case of remainder theorem. Remainder theorem itself is very straightforward. That being said, we're gonna do 2 examples that are like just no-brainers kind of thing, really, really easy. And then we do another example that's very specific. So if you missed it, it's the kind that you probably wouldn't figure out on your own. Very few people would be able to figure out example 2 in our lesson today of like how to do it kind of thing. But once you've seen it once, it's like, oh, it's one of those types, right? Oh, it's one of those questions and this is how you do it. So you want to recognize it. And there'll be a couple in the practice set today. But the funny thing about remainder theorem is because we typically use a special case of it, once in a while there's like a random question. It's supposed to be really easy. It might be 1 or 2 marks on a quiz or a test, and it's a remainder theorem question, and people overcomplicate it and start doing all these crazy things when it's just a remainder theorem question because we only do it one day and it doesn't stand out in our minds. So I would encourage you to remember that we spent today learning this theorem called remainder theorem and thinking about what it tells us, and I suppose what other kinds of situations it might come up in. And I'm not being cryptic here. There's not some like complex thing, but it's like if you ever were asked a question that had anything to do with a remainder, I would be thinking about remainder theorem. Is this going to be the easiest way to solve it? Or on the test, if you're doing a question and the question's out of 1 mark and you're spending like 20 minutes and half a page of writing and you're writing on the back and writing on scrap paper, you're probably doing it wrong and it probably had something to do with the remainder theorem. I've just noticed this in the past, that it kind of in one ear and out the other for some people. Okay, so keep that in mind while you're practicing this stuff over the weekend. It is the special case of remainder theorem that is more important, that is really, really, really useful, but we need remainder theorem first before we can get to the special case. So remainder theorem, what is remainder theorem? What does it say? It says that, and you probably won't understand when we first read it, but once we do an example, you'll be like, oh yeah, okay, I get it, that's easy. And we'll briefly talk about why it works as well. So it says that if the function, whatever a function is, f at x, is divided by something like x minus a. So like when we did synthetic division the other day, I'm going to show you an example of this. Here's our synthetic division note. When I took f at x, okay, there it is, and divided by something like this, x plus 2. Remainder theorem is a way of calculating the remainder that you would get had you done the division, whether it was long division or synthetic. Obviously, you better get the same remainder, okay? So it's not going to tell us anything about the rest of it. It's not going to tell us anything about the quotient. It's just going to give us the remainder. This is what remainder theorem does. And so if I was dividing by x plus 2, let's go back to our note today. Okay, the remainder is if I'm dividing by x minus a, the remainder is f at a. What is f at a? That's just function notation for... Yeah, I'm evaluating the function at a, not 1, depends on what it is, a, right? Yeah. Oh, for the next one, yeah. So I put a in for all of these, but careful, it's x minus a, and I use a. I put a in for all the x values. I evaluate the function at that value, and whatever I get as my outcome would be the remainder had I done the division. So it's a way of calculating the remainder. And you might say, why is the remainder important? Like, why would we want something like that? Why would we care? But again, you'll see for sure the special case that we talk about on Monday. There's one case where the remainder, what it is super important. It's super useful. Okay. Does that make sense? Notice that it's x minus a, and I'm putting in a. And this is very similar to like when we were doing factored form. If you think of this as a factor, what makes that factor 0? So I'm flipping the sign. So like if we get into this example, let's take a look at this example. To determine the remainder without dividing, this is the trick because dividing takes a lot longer. Evaluating a function is very easy and short. What would I evaluate this function at? -1. So it's x plus 1 means a is -1, or I think of it as like what would be the x-intercept. That's not a bad way of thinking about it. And I would put -1 in the brackets, evaluate the function at -1, and that will calculate the remainder. Easy, right? Like that, like it's a simple idea. There's not much to it. So let's go ahead and do that one. -1 to the 4 is just 1, positive 1, right? 5, -1 to the 3 is -1, so this is going to be -5. -1 squared is positive 1, so this is -29. -38 times -1 is +38, plus 120, and I believe this works out to 126. And so we say, therefore, the remainder, which we remember we also call r at x, is 126. Go ahead and try the next one. So what's the value that I'm going to use this time? F at 2, positive 2, because that's what's going to make that factor, that thing that I'm dividing by, x minus 2, that's going to make it 0, right? Flip the sign, f at 2. So I'll put 2 in all these brackets. And again, 2 to the 4th is 16. 2 to the 3rd is 8. 2 squared is 4. 38 times 2 plus 120. And this one works out to... Who's got this one? 0. Anybody else get 0? Is it allowed to work out to 0? Yeah, 0 is a number. Of course it can be 0. Of course it can be 0. That's it. That's remainder theorem. That's it. There's, as I said, there's one other kind of question that we're going to look at in a minute. We're going to explore some thinking before we do that. But that's it. In a nutshell, that's remainder theorem. Don't forget about it. Don't forget about it. Any questions before we move on? You can write this down, or you can just watch, write it down later, or there's not a lot of writing. You can write it down if you like. But this is a thinking thing. We're just going to briefly explore why it works. Why it works, well, I don't think in this case will help you remember what remainder theorem is. Like sometimes understanding why helps us remember. I don't know if it would in this case. But maybe it would. It's always good to know why. It's always good to understand why. You should always ask why. But I just think it's interesting. That's why we're exploring it. So why does this work? Remember our division statement. F at x equals d at x times q at x plus r at x. But I pointed out that if d at x, the thing I'm dividing by is x minus a, then I am evaluating the function f at a. So that's going to be like, d at a times q at a plus r at a. Right? So what is d at a? Does anybody know what a minus a is? 0, thank you. Remember, we talked about that's kind of how you can think about it, how you can set it up. You're flipping the sign so that it works out to 0. So if I come back over here, I don't know what q at a or r at a is. But that's 0. Zero times q at x, 0. So this is just equal to r at x or r at a, whatever you want to call it, but like the remainder. So you can kind of see it in action happening there.
So A is like, what do you call it, the X value?
It's the x value that we're choosing, yeah.
Okay. You sub it in for the other X value.
Right, yeah. Because you could choose any value you want to evaluate a function at, right? And we're just noticing that when you're dividing, like I might tell you to divide by this. I might give you that or whatever, right? And then, but if you just need the remainder, you don't have to do the whole division is what this is saying. So here's another way that you could think about it. What if I was dividing f at x? We don't even know what f at x is. I didn't come up, there is no specific f at x. What if I was dividing f at x by x minus 5? Then that would give me, where do I have some room for this? I'll do it over here. F at x would equal d at x, which is x minus 5, times q at x plus r at x. But then if I do, if this is 0, because if I'm evaluating at 5, 5 minus 5 is 0. So again, this is 0. It's just the same thing, but times q at x plus r at x. But that's gone. So this whole thing equals r at x, which is just our remainder. And when you're dividing by a linear term, your remainder is a number, right? It's just, it's a constant. So this only works for dividing by a linear term. If you're dividing by an x squared term, it's not the same thing. But if you're dividing by a linear term, it works. Any questions on that? So that's just thinking. Think about it. If you're not sure, you could spend some time over the long weekend, over your long weekend, thinking about that. So I'm going to leave you with this question. We're not going to answer it, but I think you should answer this question. Could be part of your homework tonight. If you were asked to find the remainder without dividing of f at x when f at x is divided by 2x plus 3, what could you do? It's a little bit different from the one that we did. What would you do? How could you use remainder theorem in this case? No, I'm not. It's rhetorical. I'm not asking. So if you think you already know, good. Prove it to yourself. But I want you to spend some time thinking about that. Everybody got that? All right, we got one more question to do here. This is the type where it's really not too hard, but it's specific. And had you never seen it before, you probably wouldn't know what to do. There would be a few people who, for whatever reason, are good at this stuff, but a lot of people would just, I don't even know what this question's asking me. One thing I want to point out is, and this happened on the learning goal, but it's not your fault because we hadn't talked about this. So we'll talk about it when we take up the learning goal again. But during the lesson, we used the notation of f at x and d at x and that kind of stuff. If you look back at your learning goal from yesterday and from today, it didn't say anything about f at x. So then if you're like f at x equals this, I'd be like, what is that? What is f at x? And I wouldn't actually like take a mark off or anything in this case, right? Because as I said, we hadn't talked about it. But like there is no f at x. And same in this question. There's no f at x. Do you agree? It's talking about a function, but it doesn't give that function a name. But function notation is really useful. Giving these things a name is really useful. And sometimes we take liberties where we call things r at x without like really introducing r. Like we're like, that's the remainder. We kind of use that. But usually if you want to use function notation or you're ever introducing a new name for something, a new variable, you've got to introduce it. So before we start, if I'm given a question like this, I'm thinking it's going to be in my best interest. It's going to be useful for me to go like this. Let f at x equal that function. So I'm going to start by naming it if it's not named. And this is useful in a lot of situations because function notation becomes really useful in this course. And like I say, sometimes you might get away with using it without introducing it, but in general, the rule of thumb would be if you are using function notation, it's either got to be given that way or you introduce it, like just something simple like that.
Do we have to introduce it if we're writing the final statement? Because if we know what q at x and d at x are and what r at x is, wouldn't that imply that the other side is f at x?
Do you mean like in the learning goal?
Yeah, when you're writing.
But we don't. Yeah, well, we'll look at it next week when we take it up. But we don't use q at x in our summary statement. We just write the quotient.
Yeah.
So we say therefore f at x equals this. What I'm saying there was no f at x.
Okay.
It's a small thing. It's not a big deal. We'll talk about it later. Don't get hung up on that. But I'm doing this because it's going to be useful for what we're about to talk about. So then this says this function, which now has a name, f at x, is divided by x plus 1. The remainder is 10. What's that saying? If I divide by x plus 1, that's like f at what? Negative 1, thank you. So that's saying f at negative 1 equals 10, right? Isn't it saying that? The remainder is 10 when we divide by x plus 1. So f at negative 1 is 10. Okay, and what else is it saying? Abdul? Saying f at 3 is 46. So if I divide by x minus 3, the remainder is 46, tells me the value of this function at 3 must be 46. Divide the remainder is 10 is telling me that f at negative 1 has to be 10. In the other examples, we could evaluate the function, but this one we can't because it's got an a and a b in it. We don't know what a and b are. In fact, that's our whole point, is to find a and b. How can I use what we've written here to find a and b? What do you think?
Sub it into the other one? Or set one equal to like A or something and then sub it into the.
I think you're on the right track.
Yeah, kind of like I like to set like B to 0 and solve for A, but like we have to also set these two to equal, like the two equations.
Okay, I understand what you're saying about this.
I was saying that we could put like -1 in the equation, and then 3. So we're going to like the A value and the B value both.
Yes.
Like subtractions.
Yes. I think you're all kind of saying the same thing. What if I were to sub -1 into the function that I have? It's got A's and B's, but let's do that. A times -1 cubed plus -1 squared minus 7 times -1 plus B. And what will that be equal to? 10. I'm going to simplify this. I get 10 equals, so that's -A. And that's 1. We'll just do this. +1 plus 7 plus B. Subtract 8 from both sides. I get 2 equals -A plus B. And if I do it for the second one, f at 3 equals 46, it'll look like this. A times 3 cubed plus 3 squared minus 7 times 3 plus B will equal 46. So 46 equals 27A plus 9 minus 21 plus B. I add 12 to both sides. 58 equals 27A plus B. Do we see now how we can solve this?
And then you just set one side equal to B to find A, and then you set B into the other.
Or like you use substitution or elimination as you see fit, whichever one's your favorite from grade 10. Remember solving linear systems in grade 10? Always comes back to grade 10. Equation 1, equation 2. Yes, there we go. And we have a linear system. That's all this question is. When you get it on a test, you're like, this is the linear system question. I know how to solve this. I set this one up, I set that one up, and it's an easy linear system. Okay, so I am going to do equation 2 minus equation 1. 58 minus 2 is 56. 27 minus -1 is 28. A, B minus B is gone. I've eliminated B, divide both sides by 28, and I get 2. And I'm going to sub 3 into 1. So I get 2 equals -2 plus B. Add 2 to both sides, 4 equals B. This question, I believe, asks us to find the values of A and B. Sometimes it might ask you to state the equation. So make sure you answer the question. Equals 2. It doesn't ask me to do this, but I'm doing it anyway. Sometimes you'll have to. Right? Write out the actual equation.